Good morning, everyone. It's a pleasure to be here. As Inger said, we've done a rehearsal yesterday, but it also feels like... have you seen the movie The Groundhog Day?
Over and over.
Oh, wow, you're serious about it. So it feels a bit like Groundhog Day, where the whole thing gets repeated. Except yesterday was a beautiful sunny day in Copenhagen. And I almost flirted with the audience and said, I didn't want to be at my own talk. But today, looking outside, I'm glad I'm inside. Right, so I'm a learning scientist. I'll explain that very briefly, what that means. I've been around the world. So as a learning scientist, one of the quotes that I often like to make is by a social psychologist called Kurt Lewin. And in the 1960s, he said something like, there's nothing more practical than a good theory. I know in teaching, and in other fields as well, we talk about this theory-practice divide, but as a learning scientist, the work that I want to do is to advance practice in ways that also advance learning theory. And to do so not in controlled experiments, but in the real ecologies where learning actually happens. So you're building learning theory in the real ecologies while advancing and transforming the real practice. And that's the work that I commit to. In my talk, I'll talk to you a little bit about learning, the major debates in learning, and then I'll give you a concrete example of the work that I've done on productive failure. Right? And then we'll talk about some implications. So let's talk about what's learning. There's no conversation around anything about teaching and learning where we don't articulate what learning means. So I usually think about learning as a complex set of interactions between all these levels. You can think of learning at the neural level, synapses that happens at the millisecond level, right? So you can think of learning as synapses. You can also think of learning as knowledge acquisition, the mental models and the images and the facts and the procedures that we store using the computer metaphor. You can think of learning as social participation. How do we come to talk and interact with people? That is also a kind of learning. You know, whether you're doing it in an informal basis or you're doing it in the domains or you're doing it at work, we need to participate in social discourse. We need to interact and talk to each other, and not all of us are very good at it, including myself. And cultural. How do we come to be who we are? How do we develop the identities that we have? And these identities could just be who we are, could be as a member of our family, could be the identities that we have with our friends, could be the identities you have as a doctor or a lawyer or an engineer or whoever. Learning as a process of enculturation. So when you design your teaching and learning, what is your conception of learning? Where is your picture? Is it at the neural level? You're designing for synaptic interaction? Is it at the knowledge acquisition level? You want kids to know, not kids anymore, but you want students to know a lot of knowledge and skills so that they can apply it. You want people to participate and interact with each other in teams, or you want them to be like engineers, doctors, lawyers, and so on. So think about what is your conception of learning, because it has a lot of implication. And I'll name two of them. One, as you might have noticed, depending on where you are in your conception of learning, it happens across timescales. So when you're designing your teaching and learning, you've got to think of these timescales, because synaptic interactions take place over milliseconds. Cognitive acquisition of knowledge can take place over minutes, hours. Social participation takes a much longer time, and enculturation can take years. So when you're designing your curriculum, are you designing at all these levels or not? So that's the first question. Second, what gets optimized at one level does not necessarily optimize the other levels. I'm an engineer by bachelor's training, so I think of optimization all the time. Design and optimization is what comes naturally to me. So, for example, if you maximize or optimize synaptic interaction, it does not mean knowledge acquisition is the best, or you're going to become you'll feel good as an engineer or as a lawyer. No, it doesn't work like that. Or you could cram a lot of information and knowledge and skills into people. That means you're working at the cognitive layer. It does not mean that you'll become a good person as a social level or the cultural level. So where your focus is, or where you want to optimize, or where your curriculum is targeting, it can actually have complex interactions with the other levels. So as a designer, the question is, how do we design for all these levels? Because learning happens at all these levels. And how do we design for all these levels in ways that do not counter each other? Right? So that's a very brief conversation about learning. I'm going to go on to my research. Now, you can look at research on learning in multiple ways. My research is all about these two questions. I'm really interested in the idea, in the question of how do we come to understand something new? If you don't know a particular concept in math or science or humanities or the arts or languages, how do you come to first understand something that you do not know yet? What does that process look like? It does not deny that there's a lot of learning that happens after these initial understandings, where you develop more complex understandings and you become, through practice, deliberate practice, you become more fluent and master all those things. I'm interested in this process of initial learning, because learning is path dependent. How you first come to understand something new influences what you can do with it. And I'll share with you some experimental evidence that suggests that. Okay? The second question is the question of transfer. We know from a lot of research that transfer is rare. What you learn in one situation, be it in the school, does not transfer very well outside of school or in novel situations. Transfer is historically very, very rare, and hence the lament with our students. We know that you know this stuff, yet you are not able to use it. Why is that? Right? And it happens all the time. So my question as a learning designer is, how do we design that initial learning process such that it transfers very well to novel situations? So not only to understand that initial learning process, but to design it in ways that it transfers. Those are the two challenges that I will undertake. So now I will turn to some key debates in the field, just to illustrate how I go about answering these questions. Okay? The first debate is between seeing and encoding. Let me give you a thought experiment. Suppose you're in a movie theater and you're watching a very good, very entertaining, very engaging movie. Sitting next to you is an acclaimed director who knows how to make movies. So you watch the movie, you come out of the theater, and I ask you, did you watch the same movie as the director? What would your answer be? No. Thank you. Work with me here a little bit. Right, so, and decades of research on expert novice literature will tell you the same thing. Across the fields, given the same stimuli, experts would see very different things from novices. In fact, we know experts would see the deep structural features that novices may not even see it. So it's right there, the perceptual stimulus is right in front of you. You're showing them the formulas, you're showing them the sequence of steps, you're showing them the exact structure that you want them to see, that you are seeing as an expert. But guess what? Novices, being novices, are not going to be able to see. Seeing is not a perceptual exercise per se. Seeing is a cognitive exercise. Yet, we end up making the same assumption. So if you were trying to teach somebody something new, one school of thought is, well, I should just tell them exactly what to do. Explain it. I know it. Let me just explain it. What's harmful about that? It's like that movie. Let me just show a beautiful, entertaining, engaging movie. Again, you're making the assumption novices will see what you want them to see, and that is not always the case. So the direct implication of this is the first job of teaching is actually not to teach. The first job of teaching is to prepare the novice to see what you want them to see, to give them these proverbial eyes so that they can see what you want them to see. So how do you first prepare novices to receive, to see and encode the information that you actually want them to see? So going straight into a lecture or a direct instruction is highly problematic. So what do you do instead? We'll think about that, and I'll show you some ways. The second big theme, the second big debate is an epistemological debate between knowing something and doing something. And here you have a carpenter, a picture of a carpenter and his son or daughter in the shed. Imagine what is happening here. Suppose this carpenter told his son or daughter, hey, you need to learn carpenting, but you know what? To learn carpenting really well, you need to know your math. You need to know your number systems, you need to know your measurements, you need to know, how to do geometry and angles. So you need to take courses in math and become proficient in them, and once you've taken those courses, passed them, then you come to the shed. Next, imagine the carpenter says, well, actually you also need some physics, because you need forces and equilibria and mechanics. Yeah, please do some courses in physics too. By the way, while you're at it, some material science would be helpful, and pick up the odd 2 courses in communications and business management because you need to interact with customers and finance and so on and so forth. And when you've done all that, please come and apply what you've learned in the shed. Except that's not what happens. What the carpenter says, hey, come on with me to the shed. We will engage in the practice, in the doing of carpenting, and you will learn what you need to learn, everything that you need to learn, which is important, in the practice of carpenting. The idea here is that the modern education system, especially post-industrialization system, has artificially decoupled knowledge in the domain from the practice or the doing in the domain. And then we lament that the knowledge the students have received in schooling practice does not transfer well into the domain. It is not a problem with the student. It is a problem that we have ourselves created, because knowledge is always situated in doing. So your knowledge about whatever it is that I'm saying today is situated in the practice of listening to me, if you're awake. And that knowledge will not transfer very well. I'm sorry, I'm not in the business of practicing what I preach. Knowledge versus creativity. There is this very strong tendency, a mantra, that you need some basic knowledge first before you can transfer, you can apply and use something. And there's nothing wrong with that notion per se, except when we carry out another thought experiment. So here it goes. You're going to imagine your young children playing with Lego toys. I hope you liked Lego. I hope you had a good childhood. And now, okay, since all of you did, now imagine, go back into that time, this left half, you're all children playing with a toy. I'm going to give you a toy. I'm going to say to this group, here's a toy. I'm going to show you how to play with it. Are you watching? I show you how to play with it, and then I give you the toy. It says, play with it. And I observe what you do, including you up there. And to this group, I say, here's a toy. Do you want to play with it? I give you the toy. It says, play with it. And I observe what you do. Who do you think, what groups of kids are playing with toys? Who do you think will invent many more ways of playing with that toy? You've got to commit here. Sorry? Is there anybody pointing in the other direction? And that is exactly what experiments in developmental psychology show. Time and time again, children who are just given the toy and asked to play, they discover a lot more functional features of those toys, and they also invent many more ways of playing with those toys. Now think of knowledge as a conceptual toy. What do we do with them? We, as experts, we come to children and say, hey, I've got this conceptual toy. Let me show you how to play with it. Let me show you how it works. Let me explain to you exactly how it works. And then you can play with it. We don't do that. And that is the danger, because the cognitive architecture works in very different ways. Knowledge is a double-edged sword. How you learn that initial knowledge actually influences how creative you can be with it. It's a very simple, intuitive yet counterintuitive idea. If you think of it in terms of toys, it's very intuitive. But if you think of knowledge as a toy, it becomes counterintuitive. right? So think about that. And here I want to bring in the Bloom's taxonomy. All of you must have heard of the Bloom's taxonomy, right? It's a taxonomy of knowledge or cognitive processes. You know, you must remember something first and then understand it and apply it and then be able to analyze, evaluate, and create. Except the problem is it's been turned into a recipe for designing, which is very harmful. Nowhere near in any of the writing does Bloom says, oh, because you need to learn something new, you must first remember the facts. Nowhere does he say, you must then understand what you have remembered. And then maybe apply. Oh, wait, you'll have a long way before you can analyze, invent, and create. That's a very higher order function. That will come later. There is no temporality or sequence inherent in a taxonomy. Yet, it is how we treat it. Back to the cognitive architecture, the way we understand something new, that initial learning actually influences what you can do with it. And I'm going to show you designs where you start with the processes of application and creation, even to learn something basic. So that creativity is not something you do at the end. Creativity is embedded from the very beginning. Explicit versus tacit knowledge. And this is the idea that you're all domain experts. You have all the language, the constructs, the grammar, the formalisms in your domain. And these can be, some of it at least, can be explicitly codified. You can write textbooks about it, you can show lecture notes, you can show slides, and so on and so forth. This is the kind of knowledge that can be explicitly codified. Yet, if I throw you into real-life situations, there is a lot of coordination with what we call tacit knowledge. Something that you can't really say what it is, yet you use it. It is situated. That knowledge is situated in the practice of the profession. It is something that you've come to develop over years and years of development of your expertise. And adaptive expertise is exactly about a very good coordination between what is explicit and what is tacit. What is the implication for teaching or design of learning? Simply, that if the design of teaching learning focuses a lot on the explicit knowledge, you are actually hindering the development of expertise in your students. We need to think about designing learning in ways that help students coordinate both the explicit and the tacit aspects of your domain, of your knowledge. How do you do that? Well, we'll see. One final debate, and that is about the mind and the body. In the Western canon, at least, the mind has always been the Descartesian dichotomy. The mind is separate from the body. Although now emerging evidence both in biology, neuroscience, physiology is showing that no, mind and body are connected. The Eastern mysticism always knew that, but not in a scientific way. But the idea here is mind is not separate from the body. Mind is deeply embodied. So, for example, if you were tired, you will see the same slope, a steep hill, much steeper. So your perception changes based on your physical state. Right? If you were holding a glass of warm coffee, I will appear to you a much warmer personality than I am. Your physical state influences how you perceive me. If I were to show you, it's too early to have a glass of wine, but take a pick. Neural evidence suggests that right now in your neural circuits, not only are your concept circuits where you store representations that are firing, but also your motor circuits are firing too. Grasping circuits are firing. Although you're much too polite to actually, I don't see anybody reaching out for a glass, I can tell you there are motor circuits that are firing right now, as if you were actually grasping. Why would that be? In other words, when we store information, we're not just encoding based on static entities, we are storing in a way that couples our mental circuits with the motor circuits. In other words, knowledge is encoded both by the mind and the body. And what if you could turn it around and use mind and the body together to learn something new? It's not as simple as just learning by doing. It is a much more complex interaction that we want to advance. The use of gestures, for example, is a perfect. When you look at pre-articulate children, they use a lot of gestures because they don't have the formal knowledge. They don't have the language to talk about what it is that they want to communicate. So the body, the mind, recruits the body to make sense, to convey meaning. Even I'm doing that, right? So that's a perfect example. So how do you do this in systematic ways? How do you create situations for students, especially in initial learning, where they don't have that formal knowledge, to recruit the body to design for deep learning? Right, so I've talked about a number of things. So the challenge for designing new learning, challenge for designing initial learning, is how do we take all of these principles and embody them into teaching? So how do you design for noticing so that students encode what is critical? How do you design learning in ways that the knowledge that they learn is situated in the actual domain, in the actual practices of the domain, so that you don't have the problem of transfer? How do you design learning in ways where the explicit knowledge is deeply coupled with tacit, so that they develop both of them, not just one, usually the explicit? How do you develop knowledge in ways that creativity is embedded right from the start and not come later? And finally, you're designing an embodied experience for students where the mind and the body are coupled for a more powerful and deeper learning. And that is the challenge that I take for designing the initial learning of students. And I call this design productive failure. Okay? And the idea is very simple. Now we take a turn into the second part of my talk. The idea is very simple. We all say we learn from errors. We all say we learn from failures and mistakes. Well, actually, not all of us do. Some of us continue not to learn from our mistakes. But if learning from failure is very intuitive and compelling, why do we wait for it to happen? Imagine if you could use failure to design that initial learning, if you could bootstrap it and exactly know how to design for it, test, and use it. Just like we know light carries energy, or wind carries energy, or water carries energy. We didn't wait for it to miraculously give us power plants or solar panels. No, we said, we know it carries energy. Let's design so that we can bootstrap this energy. We can use this energy in systematic ways and make it more and more efficient. Same idea here. We know failure is powerful. Let's design for it. So here, I'm going to give you an example to tell you what exactly happens. Now, I want you to imagine an initial learning situation where children, in this case 8th or 9th grade students, are learning statistics. Now, typically, if you were learning some statistics, in this case, they're learning the concept of standard deviation. All of you know what standard deviation is. If not, this would be an interesting exercise. Typically, the way standard deviation or any other math concept gets taught is the teacher will come in, I'm the expert, yeah, I'll tell you exactly what to do. I'll show you what standard deviation is, how it's formulated. I'll explain to you the different features that are important. I'll give you some problems to solve, and then I'll go through feedback and give you more and more problems. And then maybe I'll give you some more complex projects or application scenarios where you can apply what you've learned, right? That's a typical direct instruction model. In productive failure, we know that students do not know this concept yet. They may not even have heard of the concept of standard deviation. So what we do is we start them off with a design challenge. We say, here are 3 football players. Here are the number of goals they've scored each year in the league. Your job is to design as many ways as possible to determine who is the most consistent striker of them all. Okay? Fair enough? So you don't know, you have not learned anything yet, the target concept. And you're being asked to invent as many ways of designing the most consistent striker. What do you think students would do? Ideas?
Draw the numbers.
Sorry?
Draw the numbers up.
Draw the numbers up?
Yeah, histograms or something.
Okay, a histogram, or draw the numbers up, that's one. What else? Take an average.
Maybe they will use something that they already know and then try to just apply it here.
So like histograms or taking averages?
Yeah.
Okay. Anything else? Yeah. Oh, great point. So histograms and averages would be a systematic approach. What might be an intuitive approach?
Ask Google.
Sorry.
What do you feel when you look down at the numbers and you kind of impression of?
Okay, so like eyeballing data and seeing something there, but you can't really describe what it is. Okay, I'm going to come back to somebody here.
Ask Google.
Ask?
Google.
Google, okay. Oh, what? Why don't we all just go home and let Google do all the work, yes? Right. Yeah, but we make sure for this part that Google is not present. Yes?
Ask their trainers, maybe. Maybe they know better.
Sorry, okay, there are two people at the same, so the gentleman at the back, and then you go.
I suspect that many will identify minimums and maximums.
Excellent, so minimums and maximums, good.
Ask their trainers. Maybe they know who is the most consistent striker. And there are reasons why they only score 10 and maybe they had an injury and they are still very good.
All right, so seek extra information, which is in this case not available. So they have to work with the information that is available, although that is a sensible thing to seek. Any other ideas?
Both scores above 17, for instance.
Okay, so design a criteria and say how many times you scored above this criteria. Fair enough. What else?
Maybe they don't do anything because, well, maybe they don't get the question. I don't get the question.
You don't get the question? So what about it, the question do you not get?
I don't know. I still don't know if I should come up with an answer of who's the most consistent or just come up with so many different ways of doing it.
Yeah?
At least that would confuse me. Maybe they will ask for further clarification.
Yeah, and one of the further clarifications they do ask for is what on earth is consistency? Yeah? And that's an interesting discussion that we have in the class anyways. And I have to tell them, and students, the research shows that they actually ambiguate the notion of consistency from being good. And you have to tell them that a straight F student is very consistent. And then they start to think of some ideas. All right, I'm going to actually show you what students actually do. And this data comes from thousands and thousands of students across the world, actually, from Singapore, India, Australia, Germany, Canada, US. Yeah, the whole range of data. And it's amazing how consistent this data is.
How old are you?
These are 14, 15-year-olds, so in high school. All right. So, students tend to take averages, you're right, it's a very intuitive. They may have learned it also. So some of them even take mean, median, and mode. Can you see at the back? Okay, good. But one of the principles of productive failure is to activate the knowledge we think, both formal knowledge and intuitive knowledge, that we think students have, but make the problem not solvable if they were to use that. So in this case, we know that they will use mean, median, mode, but we keep that invariant. So they try something, it doesn't work, they have to think of something else. Right? They do tallying frequency tables, and when you tally, they can say, well, if you look at the third chap, Ivan, he's either very good or very bad. So it must be between the other two, and the second one is more bunched up. So very intuitive language to just argue that, one is more consistent than the other. They do frequency polygons and box plots, again, similar qualitative analysis of who's the most consistent person. Nobody mentioned the graphs, but they love to draw graphs. So time graphs, fever curves, like a stock market, up and down, up and down. And if you ask them, what is going on here? Say, if it goes up and down a lot, it's more inconsistent. But if it doesn't change so much, doesn't fluctuate so much, it's more consistent. So that's a good way to get a feel of the problem. But if you had 100 players, are you going to do the 100 times? Can you make it more precise? Can you quantify it? Just like a mathematician would do. Right? So, okay. They love to take maximum minus minimum. And again, we know that they love to do that. And so we've kept it the same. So that, again, they try something, it doesn't work, they have to go for something else. One of the most intuitive solutions that turns up a lot of the times is this one, where they just take the difference from the previous year. So how much did it change from the previous year? And they take all those differences and then they add them up. And they say, the lower this value, the more consistent, the lower the change in the graph. Okay? Some of them also realize that the positive and the negative fluctuations cancel out. And instead of saying, well, that underdetermines the variance in the distribution, they say it's not fair. And say, take the signs away, and they just add all the magnitudes of the deviations, and they take an average sometimes, and here there's an average fluctuation, average change in this data set. And that's my measure of consistency. You wouldn't find this in any textbook in statistics, at least not that I know of. But these are very intuitive ways of reasoning and thinking, even before you've learned anything yet. Right? Very rarely, and I'm thankful nobody here suggested, because there was a suggestion yesterday, that maybe they'll start taking deviations from the mean. And as you know, that's the standard way of solving the problem. You start by taking deviations from the mean. But in this case, if you do that, all the deviations add to 0. So you're back to square one. Okay? Sometimes very creative solutions also come in. I'll let this sink in for a while. So in this case, the group of students said, imagine if you could hold the end of the graph. Then let's imagine you could extend it into a rope. Now what if we could somehow calculate the length of that rope? The longer the rope, say it, the more inconsistent. Right? And what you see at the bottom, they've divided the graph into right-angle triangles. They invoked a chap named Pythagoras from thousands of years ago, and they've taken the hypotenuse lengths using Pythagoras' theorem, and they've calculated for 19 hypotenuses the exact length of the rope of 3 ropes. Imagine that. To this day, I have not checked whether that computation is correct. Do you know why?
Do you care?
I do. I wouldn't be doing this for 15 years if I didn't. Because the real mathematics is not in the computation. The real mathematics here is in the play of imagination. It's the creativity, right? Because that's what designs like this allow you to do, is to, when you're forced in a situation where what you know is insufficient to solve the problem correctly, you have to think of creative ways. Of course, there are principles by which we design these tasks and activities so that more of this comes out. And I don't have time to go into those principles. It's not just throwing any challenging problem, but it is something that we explicitly design for. So this is what happens when you give students a chance. And all of this is happening even before they've learned anything about standard deviation. Is this useful? Do you think this is useful for them to learn something new? Let's test it. If you could hold the questions till the end, I'm told because we are recording this, so there'll be plenty of time to ask questions at the end. So we run experiments. We run several experiments, both control experiments, quasi-experiments, classroom-based experiments, something of this kind, and across a range of topics in mathematics, just to test if this works. Does the theory add up of productive failure? So in one condition, or in some classrooms, we will do problem solving, like the nature that I showed you. We'll give them students this design challenge. They'll work on it for half an hour, 45 minutes. And after they're done, we will teach them the concept of standard deviation, like you would do anyways. So expert knowledge is important. But the time at which it comes is even more important. That's the idea in productive failure. In direct instruction, it's the reverse. The teacher will teach the concept of standard deviation, go through several examples in practice, and then say, now that you've learned it, apply to solve the same problem that the productive failure students solved, the strikers problem. So it's just inverted. And we track 3 types of knowledge variables in our studies. in addition to other measures as well. One is procedural knowledge or basic knowledge. Can you remember standard deviation? Can you calculate standard deviation? Can you solve problems using standard deviation? Basic knowledge that might come out on the exam. Okay? Then we track things like conceptual knowledge. Do you understand why standard deviation is designed or formulated the way it is? Why do we square the deviations? Why not raise them to the power of 4 or 6 or 8? Why do we add all the deviations? Why don't we multiply them? And so on and so forth. What happens if all the data points are increased by a factor of 2? How does the standard deviation change? So it's very conceptual in nature. You really have to know and deeply understand what the formula is doing to be able to answer those questions. And finally, we also test transfer. Can you take what you've learned and transfer it to novel problems that require a lot more flexibility and creativity? So in this case, we would ask questions like, is Usain Bolt a better sprinter? You all know Usain Bolt, right? I'm hoping. Than Michael Phelps, the swimmer. How do you decide that? You need standard deviation here, but even you might have problems solving this problem. But it requires a lot of creativity, at least for students who have not learned normalization or standardization. Right? So it's really taking what you know, it's testing the limits of how well you can use what you know in a very robust way. So what do we find? We find that productive failure, when it comes to procedural knowledge, the basic knowledge, both just telling somebody what to do and getting them a lot of practice and application, or taking them through productive failure, both are same. Very simple. Both can develop very high levels of procedural knowledge very quickly. But where the real difference comes is in the understanding, the conceptual understanding, and the ability to transfer. And this is what I call the basic knowledge fallacy. We tend to believe that we all need to give students the basic knowledge before they can transfer. Yes, the point here is how you receive that basic knowledge influences how deeply you understand it and whether or not you can transfer it well. So it's not a question of what comes first and what comes second. It's designing the process, the path dependence of learning that influences what you can do. So just because you're giving the basics does not mean you can give it any way you want. Or take the path of least resistance and say, I will just tell you, just because it's basic knowledge. It turns out that process, that initial learning process, actually matters a whole lot. An interesting thing, which after the toy experiment should seem obvious, but at the time when I was doing this work, it didn't seem obvious to me, was that direct instruction actually constrains design ability, your ability to design new solutions. So what I mean here is, if you go back to this experiment, when we ask direct instruction students, or here, in this part, you've learned standard deviation, we know you can apply it, can you invent as many solutions? So the same problem was given to them. Can you invent as many solutions as you want, as you can, to the striker's problem, say? What do you think happened? Could they all solve the problem correctly? Yes. No problem. They could apply standard deviation. Could they go beyond it? Probably not, yes. So not a whole lot. And the same effect was found on the transfer question, where they really had to invent new solutions. So what that means is these students actually had more information than the productive failure students. They had all that they knew anyways, plus the formal knowledge. How is it that the acquisition of formal knowledge inhibits, or acquisition of more knowledge, which is correct, actually inhibits creativity? How is that possible? It doesn't make sense. Yet if you think of the toys experiment, it actually does. And so the idea is that knowledge is a double-edged sword. You need a particular way of thinking in a domain. You need the formalisms of that domain. You need the language of the domain, laws and principles and theorems of that domain. And they are important for you to solve problems in that domain. So you become a mathematician, you start seeing the world in a mathematical way. You become an engineer, you start seeing world in an engineering way. You become a lawyer, well, I don't know what happens then. You know? The idea is knowledge constrains you into a particular way of thinking. It puts you in a box. But by virtue of putting you in a box, it also inhibits thinking out of the box. And we are all very, that is a very common concept, right? Think out of the box. Well, it's not that easy. It depends on how you learned that knowledge. So the challenge for learning, challenge for all of us, is how do you design, knowing that knowledge is going to put you into a box, how do you design it in ways that at least the box is flexible? Because we know it's going to put you in a box. It's not just simply a saying, you have a file on the computer, use it whenever you want. It doesn't work like that. It's more complex. And the final counter, and this is a surprising finding, perhaps not here, but at least in some Asian countries where there's streaming of students based on abilities. People have told me, look, Manu, maybe this works only for the higher ability students. Students with a lot of mathematical knowledge and motivation and interest, and maybe they're the ones who could do this. And so we've done this work with a number of schools across the spectrum of mathematical ability distribution based on standardized test scores. We found the students who are very dissimilar in mathematics are actually quite similar in their ability to invent these solutions. And furthermore, it's what you invent actually helps you learn. We've shown that effect as well. So what matters is what you do when you're inventing rather than the pre-existing differences that you came in with. So let's now go back to that big circular the diagram that I showed you and unpack some of the mechanisms why productive failure works. Right? And remember, productive failure is about designing the initial learning when you first come to understand something new. It is not about applying what you've learned, but really, how do you come to understand something new? So what's happening? From a cognitive sense, we've not done neural studies for now. From a cognitive sense, you're activating knowledge. And you're activating not just the formal knowledge that you have, but also intuitive knowledge. How do you intuitively reason about the world? And that is a very powerful resource that students have, yet we do not use in our teaching and learning. And we need to do that more. I talked about seeing. When they generate solutions of different kinds, they can compare and contrast the solutions. They can even compare and contrast with the canonical, the correct solution. And that's when you start to see what is critical and what is not. If I want you to learn what a dog is, I cannot just show you a dog. I need to show you a variant of dog and slowly change it into a cat so that you understand where the boundary conditions are. That helps you notice. One example of the same category or many examples of the same category at best will help you induct, but that knowledge does not have boundary conditions. You need contrasts, and they help you notice. There's an awareness of the gaps. Okay, I've tried several different methods. My colleagues, my peers also have tried several different methods. Some are working, some are not. But there is some method, there is some gap that I need to fill. So there's an awareness of the gap. And finally, there's a selection mechanism. You need to be able to choose in what context, what are the correct procedures versus incorrect procedures. What are the most optimal methods versus the suboptimal methods. And those selection mechanisms have to be fine-tuned. At an affective level, there is situational interest. We asked productive failure, we asked direct instruction students before they learned the concept, before the instruction, hey, how much do you want to learn about standard deviation today? And we asked the same question to productive failure students just before their instruction. And some of them were even upset. What, I have to wait until tomorrow for the, the next lesson was tomorrow? Yeah, they're really interested to learn because they've invested so much intellectual and social effort into actually finding out solutions. Their goal orientation, in other words, is towards deep understanding, not towards problem solving per se. They are frustrated. It is a frustrating exercise to do. And teachers sometimes, being lovely human beings, like we all are, they really want to help. They want to help when they see people frustrated. And I say, hold off. Have you heard of Vygotsky? Right, zone of proximal development. If you're always operating in a zone where things are not frustrating or easy, you're probably not in the right zone. Vygotsky talked about how you need to operate in between the level where you can do things independently and where you can't. And if you pitch learning in the middle, that's where things are challenging. Not so challenging that you have no idea, but not so easy that everything is easy. Making learning easy does not ease learning, right? So you've got to be in the zone where things are sufficiently challenging, people are struggling, you've got to tell them, yes, it's okay to struggle, it's okay to be frustrated, because guess what? Experts, when they act in their domains, they are sometimes frustrated as well. Haven't you had a frustrating moment? Every day. Why do we tell children that, or kids, students, that it's not okay to be frustrated? It's okay to be frustrated, it's okay to learn how to manage that frustration and channel it in ways that are productive and persist. Social. They're working together, which is a lot of what you do in PBL as well. They're working together, they're trying to explain and elaborate, they're developing shared representations, and this is by far one of the biggest human capabilities coming through language. If you and I don't know what we talk about, we have to invent a language, we have to invent a shared meaning, and unless we have that, we can't talk to each other. And this happens particularly when students are in the zone where, in the zone of initial learning, where they don't have the formalisms to talk about the phenomena, they have to invent it, and they have to develop shared meaning. And that is cognitively a very important mechanism for learning. They're sharing multiple perspectives, and they're learning vicariously through each other's ideas and failures as well. Culturally, we want to set expectations and norms in the classrooms and in the school that failure is normative. If you're finding that you're failing initially, that's good. I must insist here that this is not failure. We're not talking about failure in exams or tests or high-stakes assessments. I'm talking about, because people are worried about that. What if I fail my exams? What if I don't pass this course? And that is not what the failure here is. The proposition here is, if you're worried about success or failing in that exam, what if I told you that by designing for failure initially, where it's safe to fail, that you will learn deeper so that the very thing you're worried about is something that you can be worried about, but less. Right? So it's the failure, designing for failure in a safe way initially when you first come to understand. I'm not saying failure is okay. No. Using it in a clever way initially is okay, and it's positive. You focus on effort and growth. The mindset theory should come to mind. And we're designing for learning in ways where there is disciplinary alignment. You're not just learning about mathematics, you're learning how to be like a mathematician. One time I went, and this happened a few times, one time after productive failure, I asked students, so how did you feel about this lesson? And you know what they said? I feel like a mathematician. It's like, I invented stuff. I mean, some of it is ridiculous, but yeah, I invented stuff. And even before learning something new. And that's what mathematicians do. They don't sit around solving problems that are already solved. They attack problems for which their knowledge is insufficient, or the community's knowledge is insufficient. From a student standpoint, we're not asking them to do new mathematics. We're just asking them to do new mathematics from their knowledge state. To them, standard deviation is a new idea. Let's get them to invent. And that's the practice of mathematics. And finally, I've talked about embodiment. When you're thrown in a situation where your knowledge is insufficient, you use your body. You use gestures, you use metaphors, you use analogy, you use language and move in ways that help you communicate. And that helps in encoding, because you're not encoding mathematics just from a cognitive level or a processing level. You're encoding mathematics cognitively, affectively, socially, culturally, and embodied. It's a confluence of all these mechanisms at play together that help you learn, not one thing. Okay? And that's what makes it highly powerful. So that's how productive failure works, I think. And there's a lot of work that's still going on. But I'm told, I'm going to share with you other studies, at least one other study, because I'm told that the Aalborg model of PBL actually focuses a lot on problem finding itself. So how do you get students to find the problems and then solve them, rather than give them the problems? Rings a bell? Okay, good, thank you. There are a lot more nods today than there were yesterday. There's something happening in Aalborg that's not happening in Copenhagen. I kid you, I'm sorry. So, independently of my knowledge of this, we had decided to do some experiments in problem finding, or problem posing as I call it. So we gave students the same data set. Instead of giving them the problem that you must think about consistency, we said, okay, here's a data set. Think about all the mathematical questions you can ask, and then try answering them. Maybe the question is about whose range is the best. Or maybe the question is whose average is the best, whose trend is the best, or maybe who's consistent. We don't dictate. You ask the mathematical question, you generate the question, you answer it. What might this add to productive failure when compared with productive failure? We don't have enough time, but I will go through a similar experiment. You've got productive failure, as I showed you earlier. The only difference with the comparison conditions is problem posing, where we don't give them the question of consistency. We just say, ask and answer as many questions as possible. And then all of them learn about standard deviation. What do you think happened? No time for intrigue. Procedural fluency, procedural knowledge, there was no difference. So problem posing and productive failure both were very high levels of procedural knowledge. Conceptual understanding. Productive failure understood the material a lot better than problem posing, which is understandable because you're going deep into thinking about consistency, you're generating solutions about consistency, and then learning about standard deviations. You're going deep into a particular target concept, whereas problem posing students were thinking about all sorts of concepts. But guess what? What helped transfer was problem posing. So the ability to invent new problems in the context of this situation and then try to solve and learn about the target concept actually helps them transfer even better than productive failure. Because you're inventing the problems. And if you think about the schooling of our students, their entire schooling experiences until they come to Aalborg is in problem-solving situations. Teachers give them the problems and they have to solve the solution. Whereas if you think of knowledge work, it's all about finding the right problems. And how do you find the right problems unless you have experiences in finding problems? Right? And that's something that we want to encourage more and more. So the work that you're doing is incredible. There is experimental evidence to support it as well. 5 minutes, all right. So like I said, I've given you just a snapshot of what productive failure is and how it embodies all of these different, and there is a way, there's a principled way. I haven't gone into the principles of design, like how do you design for productive failure in very specific ways, because not everything is productive failure. I also want to emphasize here, it is the initial learning. What happens before formal knowledge is given, right? Productive failure is what happens before formal knowledge is given, because after formal knowledge, you can apply it in a number of ways. You can solve problems, you can do projects, you can do a number of things. But productive failure is about how do you design this initial process, but you still have to do the rest of it, okay? Some implications for designing. I've talked about this. We're so used to thinking of formalisms first. I'm the expert, I can give you the knowledge because I already have it. So why don't I give it to you? Productive failure says, no, apply, work on problem solving first. Get students in this zone where they have to invent and generate solutions to problems for which their knowledge is not sufficient. They don't even have that. We need to make that shift. Formalisms work for experts. You as experts understand these formalisms, these laws and principles and theories, because you have different sets of context upon which this abstraction rests. So, Newton's law of motion, to those of who are engineering and physics inclined, makes sense because you have a range of context within which this applies, and that's the abstraction. If you give this abstraction to the student, they cannot relate it. They cannot ground it They don't ground that thing in actual life. So you need to move from decontextualized learning to contextualized learning, which I understand I'm preaching to the choir right now. Next implication is also something that is not new to you. We need to shift from thinking about practices of schooling, because they inhibit transfer. They situate knowledge in practices that have nothing to do with the workforce. So instead of designing practices in the school, you think about what are the practices in the profession? What do doctors do? What do engineers do? What do scientists do? What do lawyers do? Never mind. I don't like lawyers. I'm just kidding. Enough of law jokes. My best friend is a lawyer, so I give him a hard time. And finally, content-driven. We focus a lot of content. Students, somehow as experts, we feel that we know so much and we need to give it back to the students. But guess what? Knowledge in the domains is going to increase exponentially. It is increasing. Engineers need to know today much more than what they needed to know when I was an engineer 20 years ago. You know, and this is going to continue. What are we going to do? Keep cramming all that content into the curriculum? It's not possible. I did a thought experiment with medical doctors because I work with the medicine program. And I asked a general practitioner, if I were to give you a 19-year-old high school graduate, how many years would it take for you, if you had full control over this person, in a good way, to turn out a reasonably good general practitioner? What do you think his answer was?
12 years.
12 years.
2 years.
2 years.
6 weeks.
6. A lifetime. His answer was 2 years. So if this guy were to, or girl, were to shadow and he could teach this person through apprenticeship, he would take 2 years. What it takes is ranges from 6 to 10 years or 12 years even. And the simple point here is what the knowledge and skills that are needed in the profession are a small subset of we as experts we think we have to give our students. I'm sorry to disappoint you, but your knowledge is important, but not to the point where you have to give everything. You have to design. If you design from the practice standpoint, you really have to think not just how to teach, but also what to teach. And that is a critical question that we don't spend too much time thinking about. I will end by thinking about this incommensurability between learning on the one hand and performance on the other. These two are not the same thing. You can have high learning and high performance, like perhaps in PBL. Students are trying to solve these projects, and they're also learning deeply as they are guided through this problem solving. And we can call that productive success. Learning and performance are aligned and nicely coupled. We can also have high learning, but low performance. Students are not being able to solve the problem correctly, but there's something in that struggle and exploration and invention and generation that makes for deep learning. I call that productive failure, because there's an initial dip in performance. There's sometimes there is no learning and there's no performance. It could be fun, but I think we don't want that. Right? It's good to engage in unproductive failure. I do that all the time, but not for teaching and learning. But the most dangerous beast of it all is unproductive success, when there is an illusion of learning in high performance. And that's something we need to be afraid of, because that happens a whole lot. Right? So with that, I thank you for your attention, and I think time is now to take questions if you have.